Hey everyone, so today I want to share a quick example on the quantum harmonic oscillator, and specifically how to apply the raising and lowering operators to find stuff like the expectation value of position and momentum and position squared and momentum squared, which are very important quantities. And so in this case, I have this kind of ugly superposition of states, and I want to figure out what the expectation value of position is. And so the way I'm going to do that is by using these raising and lowering operators, which are also known as creation and annihilation operators, which I think is kind of like a dramatic name, but I guess it's also kind of cool. And so to do this problem, we're going to begin by writing out what we're actually going to do. So, we want to find the expectation value of the position. And to do this, we're going to sandwich the position operator, x hat, between our bra psi and our ket psi. And that's what we're going to replace here. And so we're going to start first by replacing the x operator in terms of an expression in terms of the raising and lowering operators. And that's what's actually going to allow us to act on the state. And so we'll keep this in terms of psi at first. I'll write this scalar quantity, so we'll be able to pull it out nicely. And then I'll write the raising operator, which I like to remember because this, the Hermitian conjugate, the dagger sign, kind of looks like a plus, and so I just think of it as raising. And then we're going to close our inner product here. Awesome. So now the next step is to actually apply this state over here. And so we're going to have to be careful with this. I would say that these problems are not that hard, but it can be very easy to not be, super neat and get lost in the small calculations that you have to do, especially since these operators don't commute. So I'm going to pull out the constant, and then I'm going to write out my my bra. So I'll start by 1 over root 3, and then I'll write it like this. So I'll put the root 2 here, our bra of the 0th state plus the bra of the first state, and then I'll write my operators. So these can often be pretty space consuming, so it's important to keep that in mind. And then I'll close this out with our kets. So we just had just enough space to write it out. And so I'm gonna make this a little bit nicer by combining these 1 over root 3s. And so we should get something like this. I guess I'll write it like this. 1 over 3 square root of h bar over 2m omega. And then everything else. And so the way I'm going to think about doing this problem is essentially I'm going to consider the fact that I'm going to use the idea of orthogonality of states. In other words, if I have an inner product, something like this, where, they're different states, these different states are orthogonal to each other. And so in the same way that when we do a dot product between two vectors that are 90 degrees from each other, the dot product is equal to 0. The same thing applies here. The inner product of two different states will always be 0. And so you'll see why this is relevant. Essentially what's going to happen is we're essentially going to carry out, this horrible distribution of these terms, and we're going to figure out which ones are going to give us orthogonal sets of inner products and which ones won't. And the ones that won't are the ones that are actually going to contribute to our final answer. And so I'm going to be explicit, and I'm going to write out, the combinations in a specific way. And so I'll begin by considering the a hat terms first. So I'll write these with this color of red, and I'm going to check every combination. So for example, let's start with this. And so we'll begin by writing, for example, root 2, bra 0, and then I'll place this a hat dagger, or the raising operator, in between, and now we have to close this. And so we're going to close it, for example, with the first term over here. So I'll write the root 2 outside. It's just a scalar, so I can move it outside. And we can see that, okay, we have 0, 0 here. Awesome, this seems like it's going to close. But now let's consider what the raising operator does. So if we check over here, maybe I should have done it in blue. When we check the raising operator, we see that it raises the state number. So for example, if I apply the raising operator to my 0th state, I'm going to get an eigenvalue of the square root of n plus 1, n was 0, so I'm going to get square root of 1, which is just 1, so I'm going to get 1 times the n plus 1 state. In this case, n was 0, so I'm going to get the first state. And so what we can see is that when we apply the raising operator here, it'll end up sort of mismatching the states. So if I write it out explicitly, I'll combine the root 2's into 2, and I'll get 0 here. And then when I apply this raising operator, I'm going to get a 1 over here. And now this is orthogonal. So this whole term will be equal to 0. That's really important to keep in mind. And so when you're first beginning to these problems, I highly recommend to write out each term explicitly and to sort of see, actually go through it and see which ones are mismatched. And then once you have more experience, you can sort of see this beforehand and skip a lot of the steps. But for the sake of, being clear, I'm going to go through it. And so, awesome. The first sort of terms we've taken care of, that's going to be equal to 0. So I think now I'll write the next term. So the next term that I'm going to take care of is this first term over here. Again, the raising operator, and now the 1 over here. And so let's see what happens. I'm going to put root 2 here, and try to guess what's going to happen. Is this going to work out? Hopefully you say no, because here we're applying the raising operator to the 1 state, which means that this is going to become a 2 over here, and it's definitely not going to match the 0. And so you can already predict kind of that once we start dealing with the lowering operator, maybe this will give us a complete product. And so very well, we have already dealt with the first bra and the raising operator and these two. Now let's work with the 1 bra. And so I think I will do that by erasing this. So we've already taken care of those. Let's go back over here. Let's write these out in blue, I guess. So we have our 1 state. We're going to sandwich our raising operator again. And now let's consider this one over here. So again, I'll write the root 2 outside. And let's check this. Well, we are raising, we're using the raising operator on the 0 state. So what's that going to give us? Well, we're going to get a 1 over here. And this is going to be raised to the first state, and the eigenvalue again is going to be 0 plus 1, 1 here, we have a root 2 outside, this is just equal to 1, so overall we're going to get 1, 1, and then root 2. And since the inner product between 2 equal states is just equal to 1, this will overall just be equal to the scalar root 2. And so hopefully that sort of makes sense. Again, once you get more experience and more practice, you'll just be able to sort of jump from here to here. But I think it's really important to sort of highlight the steps in between. I think it adds a lot of clarity. And so what we can do now, I think, is let's, erase this. And let's just say, all right, we have a root 2 so far. So let's say I accidentally zoomed in. There we go. We have a root 2 so far. Awesome. So now let's keep going. So we've done the first one. We've done 1 raising, and then this one. Let's do this one over here. So we're going to have plus 1, the raising operator, and then 1 over here. Is this going to give us like a non-zero answer? And the answer is no. Let me think. Double negatives, I don't know. This is going to give me, of course, 1. In this case, if we want to find the eigenvalue, it's going to be n plus 1, n is 1, so we're going to get root 2. And then 2 over here, this doesn't match, this will be equal to 0. And so we can say that that term will be 0. Perfect. And so now we've done all the raising operator permutations. And so now let's look at the lowering operator. So again, we're going to go back to, let's do this in green. We're going to go back to the root 2. Actually, it'll probably be, for consistency, it'll be better to maybe do this one. All right, so we're going to start with root 2, the 0 state, and now we're going to use the lowering operator. So we're going to have the lowering operator, and then we're going to apply it to the 0 state over here with the root 2. Is this going to give us a non-zero result? And the answer is no, it's going to be 0. And the reason is because when we apply the lowering operator on the 0 state, this is really important. If we calculate the eigenvalue, well, n is just 0, and if we check over here, we're going to get the square root of 0, and then the square root of 0 is just equal to 0, so it just kills off the state. And so sometimes it's being described as sort of like a ladder. I think Griffiths uses this analogy, and so this is sort of like the bottom rung. And so if you apply the lowering state to the lowest state, you sort of kill it off, and it just becomes 0. And so we can immediately tell that if you happen to have a lowering operator acting on the 0 state, that'll just give you 0. And so this state is just going to die off. Awesome. So we've done this, we've done this. Now we have to do this state on the first state. So let's write it out. We do this. And so, this can be kind of annoying sometimes to manually go through each time, but once you get more practice, you can definitely optimize this a lot more, and you can notice patterns. All right, so is this going to give us a complete sort of like a matched inner product? The answer is yes, because we're applying the lowering operator on 1 here. And so this will give us root 2, 0. And then when we apply the lowering operator, we're going to have the square root, our eigenvalue is going to be a square root of n. N is 1 here, so we're going to have 1. And then this state is going to be 0 now because we've lowered it. And so, 1 is just a scalar, so this will become the square root of 2, 0, 0. But then 0, 0, this inner product is just equal to 1. And so this whole thing will just be equal to root 2. And so we can just write there. So far we have 2 root 2's. Perfect. Let's see if there are any other non-zero terms. So very well, we've done all the ones related to this bra. Let's now check the 1 bra. So let's go back to blue, and we're going to have bra 1, lowering operator acting on this, so 0 and then root 2. Is this going to give us anything? We can now see that we have the lowering operator acting on the 0th term, or 0 state, and so this is going to kill it off, and so we can immediately discard it. Perfect. And now finally we can see that our last term is going to be this one, and this one. So it'll be 1, sorry, I'm just erasing that, lowering on 1, and hopefully we can see now that this will also not work because this will be lowered down to the 0th state. And so these will be mismatched and it won't contribute to the overall sum. So overall, we get these 2 square root 2's, and so what we can write is 1 over 3 h bar over 2m omega times 2 root 2. And we can simplify this a little bit more. This root 2 cancels out with this 2 here, and so we're overall going to get, let me just clear that up, we're overall going to get 2 over 3 square root of h bar over m omega. And that is our answer. And so in this video, I've gone a little bit slow. I've sort of gone through each step, and you can imagine that once you start introducing stuff like x squared, or momentum squared, or x times p, like all these things, they start to add up very quickly, like how many terms you have. And so it's important to get practice and to sort of see these patterns of, okay, I'm applying the lowering operator to the 0 state. I can just skip that because it'll just kill off the state. And so I hope that this video was helpful. And I will be happy to make more, practice videos on this. And yeah, thank you very much for watching, and feel free to ask any questions. Goodbye.